As we all know, the number pi holds a very special place in our imagination. And one can probably write a whole history of mathematics with a thread of how our idea of pi has evolved over time, and that will connect all the great figures in maths and science in general, from Archimedes to Madhava, Euler, Ramanujan. And the latest addition to the story seems to have happened in Bangalore itself. So we are looking forward to, we have to tell us this story none other than the person behind the work, Professor Aninda Sinha, who is a professor at the CHEP and IISc, Indian Institute of Science. He did his PhD in the University of Cambridge, and then was a fellow of Gonville and Keys College before moving to Perimeter Institute in Canada for his second postdoc. Then he joined IISc in 2010. This is just a brief summary introduction. He has won numerous awards, including the Mayhew Prize from University of Cambridge, the Swarna Jayanti Fellowship, Bhatnagar Award, and the ICTP Award from ICTP. And he's also a fellow of the Indian Academy of Sciences. So, Professor, moving on to.
Am I audible? Okay. So, thank you very much for the invitation and the kind introduction. It's a pleasure to be here. So, I'm here almost every day, but my role is different. So, on the other days, I'm here as my wife's chauffeur. But now it's a pleasure to actually interact with you as a scientist. So I'm going to tell you about some work that we've been doing, and this has been evolving over the last several years. It's not a one-off. And I'll try to communicate where the physics thinking behind this story comes about. As Biman said, it's about pi, but as will become clear in my talk, the central role is not really pi. So anyway, so the title of my colloquium is Stringing Madhava's Pi, and QFT perspective. QFT stands for quantum field theory. Don't worry if you don't know any quantum field theory. I'll take you through it, whatever is necessary for you to understand this talk. This is a talk which begins with ancient history, so we should have ancient people. Now, as the person on the left is, I believe, an artist's impression of Madhava. So I wonder how many of you recognize the person on the right? Yeah, so the person on the right is Euler. And Euler invented many things. Madhava is not just known for his pi series. He came up with the series for sine and also arctan. But the thing to note is the century where he lived in the 15th century. And he is recognized as the person to have come up with the first infinite series representation for pi. As you can make out, the first term in this series is 4, so there has to be large corrections to make it converge to 3.14 and so on. And this series is going to play an important role in my talk. Euler invented a lot of mathematics. Euler was very prolific. Amongst the many things that he invented was what is called the zeta function. This is called the Euler zeta function, and the complex analytic continuation of this Euler zeta function plays a role in the Riemann hypothesis, arguably the most famous unsolved problem in mathematics. One thing to notice, pi here in this form of the series, the terms behave like 1 over n, and the reason why this converges is because of the alternating sign. So this is a conditionally convergent series. Whereas here, zeta of 2, it behaves as 1 over n square, so that is going to be convergent. And the 1 over n square was set to Euler by his tutor, Bernoulli, to try and come up with a closed form expression, and it goes by the name of the famous Basel problem. And so when k is 2, the answer is pi square by 6. So there is a pi there as well for even zeta functions. So what is the link between these two? And the link is going to be via physics. In particular, in my story, it will be via quantum field theory. So there are two main players, and it's fascinating to learn the history behind the Madhava series. So what is the proof that he came up with the first infinite series representation? So the earliest known record in modern times was by the British historian Charles Wish, and this was published in 1832. He reviews four books, four shastras. One of them is what is called the Tantra Sangraham, and this is an astronomical treatise written by one of the mathematicians in the Kerala School of Mathematics. He wasn't a direct student of Madhava, but he was one of the well-known mathematicians in the Kerala School of Astronomy and Mathematics. This book was published in 1501. And as you can make out here, the heading is on the Hindu quadrature of the circle and the infinite series proportion of the circumference to the diameter. Now, I should make out that this has got nothing to do with religion. The Indians were uniformly referred to as Hindus by the British. So, Madhava was setting up what we understand as the modern version of calculus. And so, in fact, he didn't write down the numbers in the form that we are familiar with. He actually wrote it in the form of a Sanskrit sloka. And this got translated, and if you reinterpret what this actually means, it will give you the series that I showed you in the first slide. And in fact, very fascinatingly, in this sloka, there is also a formula for the remainder term, and that's remarkable, because it's not just the series that converges to pi, but if you truncate it, what will be the remainder? He had a formula for that as well. So the other main player is Euler. So Euler's oil portrait, if you look at very carefully, so there are two funny things to notice here. One of them is that he's, for some mysterious reason, he's wearing a towel on his head. So nobody knows why. But if you look more closely, you will see that his right eye is squinted. So in fact, his right eye was already damaged by that time when he sat for this oil painting. And Euler invented a huge amount of mathematics. So he invented what we identify as E. He invented this Euler's equation, which relates E, pi, the imaginary number, and 1. He invented the gamma function, which will play a vital role in my talk. B is the Euler beta function, which is going to be a particular ratio of gamma functions, which I'll introduce later on. And I have already introduced the zeta function. And something that is probably not that well known is that he popularized the notation for pi. Okay, so he collaborated with so many mathematicians during his time that pi became popular as 3.141 and so on because of his work. And then he went blind towards the end of his life because of a botched up cataract operation. Now, it's not very clear whether it was a botched up cataract operation or whether he did not take care of his eye properly. He was already sort of half blind because his right eye was defective, but he went blind in both eyes after this operation. He lost his house in a fire and his wife died, but his productivity after all this increased. He became blind, but he used to dictate mathematics to the scribes who used to write it down. So his mathematics was done in his head. And he produced so much mathematics, which amounted to around 25,000 pages. His work continued to be published 50 years after his death. And this beta function that I told you about is going to play a very important role in our story. It's a particular combination of gamma functions. So my work is going to be based on this particular article that we put out earlier this year, which was published in Physical Review Letters, and this was written with Arnab, who is a postdoc with me in IISc. But it actually builds on several other works that we have been doing over the last several years. In particular, there's another letter that we wrote with my graduate student, Ahmadullah Zahed, and another postdoc, Prashant Raman, which was published. This was a longer article, so it was published in JHEP. And it's a funny story. The article that we sent to JHEP was already 86 pages long, and the referee report came that we were too succinct in many of our explanations, and our writing style was suitable for Physical Review Letters, but not for JHEP. So we had to expand it even more, so it was close to 100 pages by the time it finished. And this line of research actually originated from exploring critical phenomena. So critical phenomena is something like if you wanted to look at the phase diagram of water, there's a critical point, and you could actually calculate observables like the specific heat of water at the critical point. And this is what we were looking at using quantum field theory techniques. And this was developed with Rajesh Gopakumar and two of my graduate students, Apratim Kaviraj and Kallol Sen. Kallol is there in the audience somewhere. Yes, there. And this was also published as letters earlier. So after our work came out, it got some traction. It was covered in Scientific American and also this number file channel on YouTube. And they began to describe our work in some very, using some words that at least wouldn't have struck us. So in particular, they reported it as two physicists having come across an infinitely many novel equations for pi. And so why they reported us as having discovered an infinitely many novel equations, I'll explain in a bit. And I should say that the reporting in the press was, with pi as the focus, didn't come from us. It was after we published our paper, we sent our paper to our divisional chairman, who is a mathematician, Kaushal Verma in IISc, and he sort of had nice things to observe, and he said that, oh, this is very interesting, so why don't you actually do a press release on focusing on pi? So that's how the pi story originated. And in fact, ironically, our paper was not about pi. So in fact, the formula for pi was the last paragraph, and so PRL has changed its format. It has introduced something called end matter, so you can write longer articles, so you can actually publish an appendix with the article itself. So instead of squeezing everything into 5 pages or whatever the word limit was. And for a while, we even debated whether to relegate this formula to the supplementary materials. So it was something as an afterthought that featured in the main text. And in this formula, so this is the formula that we presented, and I will discuss this formula in a bit. I'll explain the notation as well. We talk about the fact that when a particular term or particular parameter in this formula goes to infinity, it becomes precisely the Madhava series. And the Madhava series is notoriously slow to converge. So in fact, if you try to calculate pi up to 10 decimal places or even lower, to 10 decimal places, it takes around 5 billion terms in this series to converge. Whereas with a particular choice of this parameter that I'm going to explain, it will take around it will take around 30 terms. And I should also make a disclaimer that our claim of fast convergence is with respect to the Madhava series, and it is not the fastest converging representation of pi by a long stretch. So in fact, there are people who work on computational mathematics who actually try to come up with algorithms where you can get pi very fast. So if you go and look at Wikipedia, you will see Borwin brothers, Chudnovsky algorithms and things like that, where actually you can get pi to 10 or even 20 decimal places within 2 or 3 terms in that series. So what is this series? So this was a byproduct of our research, which I'll explain in a little bit, but let's first look at the formula. So this formula is, again, like Madhava series. The first term in this formula is 4, and then there is an infinite number of terms. So 1 over n factorial, so hopefully everybody knows what a factorial is. It's just a product of successive integers starting with 1 and ending at n. Then there is a particular 2 rational terms. Now the funny thing is that there is a parameter lambda. I have not told you what this parameter lambda is. I'll explain that in a bit. And then there is this particular notation which may not be familiar. So I need to explain what this notation also means. So this formula arises from quantum field theory considerations. And so let's go through the formula a little carefully. So first thing is that in this formula, lambda could be any complex number, doesn't have to be a real number. So long as the real part of lambda is bigger than -1, it's a free parameter. So in that sense, you put in any lambda that you want, satisfying this condition, and it will give you pi. So if you sum over all the infinite number of terms, the dependence on lambda disappears. Okay? This a subscript n that appears in this formula is what is called a rising factorial. It's a generalization of the usual factorial. A rising factorial starts with a plus 1, a plus 2, etc. If you put a equal to 1, it just becomes the ordinary factorial. Okay? So these are the only things that you need to know so far as this formula is concerned. Because it's a product of, it's a polynomial in A, it will become a polynomial in this quantity. So if you choose lambda to be a rational number, you'll just get rational numbers as the output. And this formula does not exist in the mathematics literature, so we actually put this up on, so how would you know that you have come up with a new formula? So, because pi has been studied for centuries. So if you claim that you've come up with a new formula, you have to do it with care. So we put it up on Math Stack Exchange, and it lay unanswered for a long time. And then after our paper got traction, various people started wondering whether this formula was actually new or not. So there's a website called Math Overflow, and there are serious mathematicians who actually work or make posts there. So there are experts on pi who started discussing among themselves that they had never seen this kind of a formula before. In fact, there are some famous mathematicians as well who started discussing. It was fun to watch because we are not mathematicians, so we don't actually have the credentials to make any comments on those posts. So we are just bystanders. We can just see what they're discussing. Okay, and not all the discussions were really pleasant, so let me tell you that. So, anyway, so the outcome of this formula, which I'll show you in a bit, is that if lambda is very large, if you truncate up to a particular term, then the summand actually behaves exactly like the Madhava series. It approximates to the Madhava series. So this formula interpolates the Madhava series to a faster converging quantum field theory inspired one. And something very interesting happens, that if you are restricting lambda between this range, then each term in this summand is negative. And this is unlike Madhava series. So if you remember, there was a minus 1 to the power n in Madhava series. So that was an alternating series. Here, actually you get some series with definitive sign properties. And there's an even more bizarre fact. So because I said that real part of lambda is greater than or equal to -1, so let's just put lambda equal to some integer multiple of pi. And let's truncate this series. You are going to start getting rational approximate polynomial equations for pi. And the solutions to the polynomial equations will approximate pi. Okay? It's not easy to see. It does work out to be. I'll show you what the rationale behind our way of thinking about it was. No, it's not easy in that way. The way that you see it is via dispersion relation. So I'll talk about that towards the end. But there is a more direct proof that was discovered by mathematicians. So after our work came out, there was a direct proof of this formula without using dispersion relations that was given by the Swedish mathematician Hjalmar Rosengren, which uses partial fraction techniques. So that makes it obvious that it's lambda independent.
Starling approximation for the Poca.
Yeah, no, that is not going to help you, no. So let's play some games. So as theorists, this is my lab, Mathematica. So I think lots of you use Mathematica, so you can actually take your formula and you plug it in. So for example, here I've just put lambda equal to 5. You can put whatever you want. And then you'll get, so let's consider the first 5 terms. As I said, all the terms begin with 4, and so these are the first 5 terms. And as you can make out that if you take the total, it's 3.141, so within 3 decimal places, it agrees with pi. And then you can place lambda to be something very big. You get a series of terms, and you ask it to calculate the decimal value. The decimal value actually agrees with whatever you get from the Madhava series. So that's what I was telling you, that if lambda is very large, then each term actually becomes equivalent to what you get in the Madhava series. And the Madhava series converges very slowly. So in fact, with 5 terms, you don't get 3.141. You don't even get first decimal place convergence. The Madhava series up to 5 decimal places is 3.3. And of course, now that you have a formula, you want to do something even more. So this is a demonstration of 500 decimal places agreement. So now you can use some parallel computing tricks on Mathematica. You can do parallel sum. And then you can actually compute the series up to some very high accuracy. This is some random value of lambda that I've chosen. It gives you pi. And then Mathematica has inbuilt several thousand places It knows about pi up to several thousand places, so even up to 20,000 decimal places Mathematica has stored. And so you can compare that, and you can see that it agrees. Okay? So at this point, as physicists, of course, we want to declare victory. And I should tell you that this kind of addiction, we are not alone. So if you look at Newton's work on pi, Wikipedia says that Newton himself used the arc sine series to compute a 15-digit approximation to pi, and saying that I am ashamed to tell you how many figures I carried out these computations, having no other business at that time. So, of course, at this point, we want to declare victory. Yes?
This comparison, like how sensitive it is with lambda, you have chosen like some particular
Some
so
random,
suppose I just
yes.
say 3916 by 12 or
Yes.
something.
Yeah, so depending on what value of lambda you choose, so if your lambda is very big, then the number of terms that you need to get convergence is also going to increase.
Okay.
So
but like
it
if I
actually,
just change it by epsilon, you
then it won't change.
like
No,
it-
I will show you. I will show you. That's a good question. I'll show you. That's a very important question, in fact. Yeah, just keep that in mind. So at this stage, we have Mathematica and we are physicists, so we want to declare victory. So this is a meme. So in mathematics, so this is a supervisor talking to a student. This isn't a proof. You can't have a whole step that just says Mathematica said so. But in physics, we would say that what a waste. Half of this proof could have been replaced by Mathematica said so. Okay, so just to point out that so this was using physics techniques, dispersion relations, which I'll tell you in this talk, but there is a more direct method using partial fractions, which was discovered by mathematicians Hallman Rosengren after a paper came out. And this came out just earlier this month. So this is a picture that we have. So this is just to give you something to keep in your mind. So, so this is our series. So on the x-axis, we have the number of terms. And the number of terms I call difficulty, because the larger number of terms, the more difficult it is for you to do some calculations. On the y-axis, I have this extra parameter that I've introduced, which I call the flow parameter, lambda, because it is the same value regardless of what value of lambda you choose. And depending on what choice of lambda you make, you might have to retain a larger number of terms to get the same number of decimal place convergence. Okay? So this here, if lambda is minus a half, then this actually corresponds to exactly the kind of calculations that you would do using string theory. In fact, this is the string worldsheet calculation. If lambda is somewhere in the intermediate regime, I will argue that this is what you would encounter if you did quantum field theory calculations. Whereas if lambda was very large, you again get a slowly convergent series, which is the Madhava series. So in some sense, it's as if this kind of a picture is trying to explore an extra coordinate and trying to find the shortest geodesic distance in that coordinate. So that's why I call this the holographic pi. I mean, of course, I'm not suggesting that there is some deeper quantum gravity picture behind this. So what exactly were we trying to do? So contrary to what you may think, it was not a pi-n to string theory. So pi-n means a song of praise. Rather, it was trying to address a pain that exists in the minds of many practitioners of string theory right from the origins. And I'll try to explain this story. So let me try to explain this. And for this, I need to explain a bit of quantum field theory. And it'll be very limited. So it won't be a lot of quantum field theory, so hopefully you'll bear with me. And so that is the reason why we have field theory in the title of our paper. The paper read Field Theory Expansions of String Theory Amplitudes. And you'll see that we were actually looking at a quantum field theory picture of string theory. So let me begin with a 5-minute crash course in quantum field theory so that I don't lose the audience. So we will, as I said, the amount of quantum field theory we will need is very little. We'll just require tree-level quantum field theory. So QFT stands for quantum field theory. If you're a quantum information theorist, it stands for quantum Fourier transform, but here it stands for quantum field theory, so don't get confused. And so what is quantum field theory? We know Maxwell's equations. There we talk about the electromagnetic field. We also know Einstein's equations. There we talk about the gravitational field. In modern parlance, the notion of field is important to be consistent with Einstein's special relativity. Otherwise, you'll have the unfortunate feature of having immediate action at a distance. That is the problem with Newton's laws, because Newton's laws does not tell you anything about if you perturbed an apple here and another mass here, how long it will take for that disturbance to propagate. The fluctuations of these fields, and these are called the quanta, are identified as particles, and this is a technical comment. When we have flat space-time, and this is an approximation, of course, we know as far as we can say that we are living in an expanding universe, so we should be doing quantum field theory in an expanding universe. But for all practical purposes, right now the cosmological constant is very small, so we can approximate space-time as a flat space-time, and then we can label the particles by the momenta and spin. Okay. The mass of the particle is related to the quadratic invariant made of this 4 momenta. So this is something that you learn in special relativity. So special relativity, if you remember your undergraduate days, there is a momenta p, there is an index mu, and then you form p mu with a particular kind of a matrix, which is called the Minkowski metric, and you get an invariant. So typically, what we do is the following. So we start off by specifying the spectra of particles in free field theory. And just to get the point, so let's assume that the spectra is of this kind. And for simplicity, let's just consider spin 0 so that we don't have to worry about the spin of the particle. So you can think of this as the Higgs boson, for example. I don't know. I mean, there could be other scalar particles. This is just a toy model, so I could do whatever I want. So you have some particles of light masses. So let's call them phi 1 and phi 2. And you could have particles of heavy masses, psi 1 and psi 2. So the light masses, this is what I will call infrared physics, and the heavier particles we will call ultraviolet physics, high energy physics. If the energies are low, we don't care about the other particles. So for example, suppose this blue dotted line tells you how far in energy you can probe in your experiment, then you would have thought that we really don't care about these heavy particles. And you would be almost right, and this approximation goes by the name of effective field theory. Almost is an important word. It's not, you're not quite right. So it's not just sufficient to just throw these particles away. Okay. So after we specify the spectra, what we do in quantum field theory is we specify interactions. For example, in quantum electrodynamics, we specify how the electron and photon interact and what the strength of the interaction is. So these are things that we put in by hand. And then mainly in high energy physics, we calculate the probability of particle scattering, and this is given by what is called a scattering amplitude. So the unitary operator that takes the incoming particles to outgoing particles is what we refer to as the S matrix. And what we do, and this is something that we learn in a first course in quantum field theory, is that we use a machinery of Feynman diagrams. So what is happening? So there are two kinds of particles here in this picture, the red particle and blue particle. So red particle comes in with momenta p1 and blue particle comes with momenta p2. There is a virtual exchange that happens, and then it again becomes the red particle and blue particle. This kind of a diagram here is what is called an exchange interaction. It's called an exchange interaction simply because there is something that is getting exchanged here. So we do the calculation in momentum space, and we calculate the probability amplitude. So at each of these vertices, each of these point of interactions, there is a coupling constant that again we specify by hand. And the probability amplitude for this process that happens works out to be g squared, because there are two vertices, g times g is g squared, and divided by, as I said, that it has to be relativistically invariant. So you have to construct a quantity that is invariant in terms of p1 plus p2. And why p1 plus p2? Because there is momentum conservation that happens at this vertex. And so the relativistic invariant that we compute is what is identified as S. This is what is called a Mandelstam invariant, but for us, just remember the notation S. So an exchange like this is going to be S. But there is another diagram that we can consider, which is actually the red particle interacting with the red particle through another exchange, and the blue particle going to a blue particle through this exchange. So here what happens was the red particle and the blue particle interacted and gave this virtual particle, and here it's the red particle that remains the red particle through this virtual exchange. Okay. So in this case, again applying momentum conservation, P1 momenta comes in and P3 goes out. So the momenta here in this virtual leg is going to be P1 minus P3. Again, you construct a relativistic invariant and you call it another name. This was P1 plus P2, the relativistic invariant of that. Here you construct P1 minus P3, the relativistic invariant of that. So those are conventionally called SNT. So these are called, this in quantum field theory is called the S-channel process, and this diagram is called the T-channel process. And the total probability amplitude is given by the sum of these two. So just look at these two quantities. This is the simplest diagram that you can calculate. You immediately observe that this amplitude is invariant if I exchange S and T. The invariance of this amplitude under S and T is what is called crossing symmetry, and crossing symmetry is very important. But the key fact is this: we add both channels when we compute the amplitude. So there are two diagrams in this example that we need to add to get the correct answer. So just remember that in this example, quantum field theory says we have to add two channels, because this channel thing is going to play a major role when we next talk about string theory. So now let's go back and ask what happens to the role of these very heavy particles that was there in my spectrum. So you would have thought that let's forget about the heavy particles, we'll never be able to excite them, so they will not affect any of our low energy physics, but that is wrong. If we had powerful accelerators, we would actually find these heavy particles. And contrary to what you may naively think, these heavy particles will leave their imprints on low energy physics. The understanding of this has a technical name in particle physics. It goes by the name of the renormalization group, but I won't go there. I will give you a non-standard explanation for how these heavy particles can explain physics, influence low energy physics. So when we do an integral, think of an ordinary integral. So integral dx, some function of x. You are allowed to do coordinate transformations on that x. You can go to a convenient coordinate variable, which will enable you to do the integral more easily. There is a similar notion that we are allowed to do even in quantum field theory. Is basically we can do an operation on the field as long as the in state, what we identify as the in particles and the out particles, are untouched. This goes by the notion that we are allowed to redefine our fields, and the observable quantities should remain invariant. Okay? You don't care about what you identify as a field so long as you know that the in state and out states are what carry the right quantum numbers. This is usually set as an exercise in a first course in quantum field theory, but if you have not done this exercise, don't worry about it. Just believe me when I say that this is true. So now let's go back to the picture of the spectrum. And let's suppose that the interaction was light particle, and heavy particle. So there's a cubic interaction. Cubic means why? Because there are three fields: light, heavy. And let's redefine this field psi 2. Let's redefine it by saying that psi 2 goes to psi 2 plus lambda phi 1 phi 2. I'm allowed to do that because phi 1 phi 2 is still a scalar. Product of scalars remains a scalar. But what happens is that if you do this substitution, the change of variables inside this cubic interaction, you're going to get an extra piece. Just replace psi 2 by this quantity here, you're going to get lambda phi 1 phi 2 phi 1 phi 2. Okay? Is that clear? So it's just a change of variables. You get an extra term. But this extra term is very important, because if you did a calculation of Feynman diagrams using this extra term, your Feynman diagram would look like this. There is no exchange. This is what we identify as what is called a contact interaction. So the physics interpretation of exchange interactions and contact interactions are very different. If you did a Fourier transform and went back to position space, these exchange interactions would be responsible for 1 over r type potentials, whereas these contact interactions, depending on the number of derivatives, would actually be responsible for positive powers of r. Okay? So the physics interpretation of these two interactions are very different. But this is then what we learn. This new term depends only on light fields, because phi 1, phi 2 were light fields. So I did a redefinition of a heavy field, and I got an interaction that only influences the light fields. So here is the imprint of the heavy fields. So even if after doing this redefinition, if I threw away the heavy fields, I still get this new term in my Lagrangian, or in my description of physics. And this is the important lesson that we learn. If we truncate the heavy fields, then the observables involving only light fields will know about these heavy guys through an ambiguity. And this is similar to this parametric ambiguity in pi. Okay, so that is the interpretation of why we must have these parameters in these, whenever you think in terms of a quantum field theory interpretation of these numbers. Which one? Yeah, I will tell you. So here, this is a toy example where I said that whenever we have transcendent, in my example, it was pi and zetas, and I said that if you have a quantum field theory picture of those, then you must have a parametric representation for those numbers. That's the lesson that we learned through this physics argument. Okay, I will tell you more in detail how the argument proceeds. Yes. Yeah, so it's not really in terms of light field. So psi2 maintains its character. As I said that we start by describing free fields. Okay, so I cannot just change the field by saying that it is psi2 going to lambda phi1, phi2. This first term is important because otherwise what I call in state is going to be different. In state and out state have to preserve their characters, otherwise it's not possible. So that's the rule. Which one, sorry?
This kind of diagram will be proportional to Z now, or like you had the Z square, right? This other diagrams.
Yeah, Z square, which one?
G.
Oh, G. This is going to depend on this parameter lambda. This is an arbitrary parameter that I've introduced. Okay, so this is the arbitrariness. So I've not specified what lambda is. Lambda could be anything. So this is, I had this clever way of pointing this out. So remember that there is a contact term that is ambiguous, but also this is important that the heavy fields redefinition actually gives rise to this parametric ambiguity. Here. No, here it is just lambda. Yeah. Yes.
So in this particular case, you're saying that this is the kind of field that
That's right. Yes. Otherwise, you would have.
keep your S and T channels same.
Yes. That's right. Exactly. The exchange diagrams are not affected. It's only these new pieces, these kind of diagrams that you add to the answer. So those answers, very important point. Those answers remain the same. Okay. So then, how do we use it in terms of pi? So this means that, as I said, so this is again putting in words that pi, if it has a field theory way of looking at it, it must have a truncated series sum with at least one parameter ambiguity. This is an important point. I'll leave this as an open problem right at the end. So the formulas that I'm going to present next are going to only introduce a one parameter ambiguity. In the example that I showed you, if there are multiple heavy fields, you could introduce any number of parameters that you want, not just one parameter. So how do you make use of this ambiguity? So obviously, the final answer should not depend on this parameter. So you want to write down some equation that looks like this. So some quantity that you're calculating, so some observable that you're calculating, some scattering amplitude. This should not depend on this parameter lambda. So you have this differential equation, partial differential equation, that the derivative of this observable with respect to lambda should be 0. I use approximate sign here because I want to work with a truncation, and if I truncate, then it can at best be approximately 0. If I kept all the terms that are there in finite series, then it will be exactly 0. So for example, let's consider, so this is your question that you asked, that what happens if I dial lambda? So here on the x-axis, I've plotted log lambda. So lambda takes on some huge range of values, real values here. And I have just truncated the series to 20 terms. So what happens is that up to some very large value of lambda, you see that the answer hugs this exact answer line. And then it climbs up and hugs the other line, which is what you would have gotten from the Madhava series. Okay, so the Madhava series converges very slowly. It has got a different rate of convergence. And that is why you get some kind of a flow between the exact answer and the worse answer, which comes from the other representation. So here you can think of it as a perturbative RG because ultimately this is going to come from perturbative string theory, this picture. But right now you don't have to think about perturbation theory. I have not introduced any coupling constant as yet. So this equation that I have written down, you can think of it as an exact equation.
So this is large lambda, right?
This is large lambda, yes.
Large lambda is just worse.
Yes, because Madhava series, remember, Madhava series was very badly convergent, and large lambda for pi went to the Madhava series. No, small lambda is, yeah, okay. So here, yeah, so I'll go back to and show you the picture. It was not as bad as the Madhava series. You are right. Even when lambda is very small, it does not really work as well. But in the intermediate regime, because I've truncated to 20 terms, it actually converges pretty well up to 2 decimal places. Yeah.
Yes, sorry for disturbing you.
Yeah.
There is any chance to see the RG equation explicitly?
The RG equation, so here this is an analog with the RG equation. So this is not really the RG equation that you're familiar with in quantum field theory. So this is the analog of what we would call an RG equation in quantum field theory.
As I am understanding,
Yeah.
some sort of each point can analysis.
Yeah, that is a good point. So yeah, so it's a good point. It requires a bit of discussion. So let's, I'll come back to this at the end of the talk, because it is a bit technical, the answer to your question. So we are now ready to discuss the puzzle in string theory. So what is the puzzle in string theory that I was referring to? So this needs us to understand a little bit about the history of string theory. And unfortunately, the history of string theory is no longer covered in textbooks. So you have to go and look at the original textbooks. So obviously the classic textbook here is Green, Schwartz, Witten. And I wouldn't say forced to read it, but Michael Green was my advisor, so I felt morally obligated to read this book. It has got a beautiful introduction. And they are very actually honest about what the motivation for doing string theory was. So if you read the book carefully, they talk about a paper that appeared in 1968 by Dolan, Horn and Schmidt, and they argued that experimental data depending on trying to explain hadron scattering told us that you should not add the S and T channels together, you should just have one channel. So this is very different from what we do in quantum field theory, where we added 2 channels. String theory says, at least this paper apparently says, that you only are allowed to use 1 channel. And this principle, where you are using only the physics in 1 channel, is called duality, or used to be called duality. There are various other forms of duality that exist in string theory, but this was the old form of duality, which goes by the name of dual resonance models. But they are actually very honest about what exactly the support behind this was. First of all, notice that the experimental data only supported small values of energy, so this S and T can be thought of as energies. And later on in the chapter, they say the duality hypothesis never had more than a slender experimental support, and the Veneziano model was merely an ad hoc way of satisfying this not so well motivated hypothesis. Okay? So this provoked me, although somewhat late, to go and look at the original paper. Okay? And the original paper, again, in the same spirit as the way that people used to write papers in older times, was also very honest. This is not really what Dolan, Horn and Schmidt actually had said. So Dolan, Horn and Schmidt were trying to explain experimental data. So this is the scattering data. Scattering data in particle physics, you'll always see bumps. Bumps correspond to resonances. If there were stable particles, the bump would be very narrow. If there are unstable particles, it would be wide. So this corresponds to some unstable particles in the spectrum. So they actually say that the correct prescription for describing this physics is actually summing over both the channels and subtracting off something. We don't really know what the something is. That is the interpretation of what they write here, which I won't read it out to you. But basically they say that if there was some additional criteria which led to the cancellation of this term and the last term, then you'd be left with only 1 channel. Historically, when you add the 2 channels, this was referred to as the interference model, and this was trashed in those days. Okay? So I should not say anything flippant because this is being live streamed, but Dolan, Horn and Schmidt were postdocs of Murray Gell-Mann's. And I don't know how many of you know about the equation between Gell-Mann and Feynman. So, yes. Anyway, so if you read this, it does seem like the authors are clutching at proverbial straws, and they do need both channels because otherwise you wouldn't be able to explain these bumps. So for a while, it was sort of, the propaganda was that string theory is very different from quantum field theory. but that is very confusing because that is not really what we understand string theory as. This is some older famous literature which was written, there's a famous physics report authored by Mandelstam which makes this distinction very precise. So this is what you would do in usual quantum field theory, you sum over two channels. In my example, there are only two channels. Whereas string theory would say that you sum over only one channel, and that the sum over one channel is equal to the sum over the other channels. Sum is you're summing over all the virtual particles that are getting exchanged. So sum means that. But modern literature for string theory has a version called string field theory, which actually says that you should be allowed to think of string theory as an ordinary quantum field theory. So now this seems like a self-contradiction. Because how can this statement and this statement and this statement be true? Because imagine that this statement was true, then this would mean that this term has to cancel on its own. And so obviously, you cannot write it as a sum of S channel and T channel. So what is missing is this extra piece, this contact interaction that I told you about. This is the contact interaction that is missing that is going to cure this problem. Another thing, from the point of view of mathematics that should be clear to you is that here, if you have poles in one of these S variables, so the amplitude is a function of two variables, S and T, it should have poles in both variables, S and T. Poles means if you put S equal to that value of the pole, it blows up. So think about poles as poles like that. So if you have poles only in one variable, how on earth are you going to see the poles in the other variable? If you just had, you're summing over, so the thing is, you're summing over things like 1 over S1, S minus 1, plus 1 over S minus 2, plus 1 over S minus 3, and so on. You only see singularities at S equal to 1, S equal to 2, S equal to 3. Where are the poles at T equal to 1, T equal to 2, T equal to 3? So that is only possible if you sum over everything, which essentially means that this representation has to be non-analytic. Okay? There has to be a breakdown in convergence if you did this calculation alone. So, and very strangely, for reasons that will become clear in a bit, you could have anticipated such representations, but no explicit representation was ever written down. So how is this consistent? So this is where we come in, and this, yes. So this picture here would tell you that there has to be a representation of this amplitude where you're summing over poles in individual channels, exactly like quantum field theory. But of course, to fix this so-called double counting problem, you would require to add this. So an answer that looks like this was never sort of explicitly written down in the string theory literature. So this brings me to a famous quote by Alexander Polyakov, who's a very famous theoretical physicist. The garbage of the past often becomes the treasure of the present and vice versa. Now, what you call as garbage and what you call treasure, you can think about mentally and try to equate various possibilities. I won't go into that. So let me just, in the last 10, 12 minutes that I have, tell you about the Euler beta function, which I mentioned right in the very beginning. So there is this Euler beta function, which in the string theory literature is what we call the Veneziano amplitude, what the puzzle is and what its resolution is. Yes. And then there is an extra term that's yes. That is going to be analytic. It's analytic except at the poles. Poles obviously this is non-analytic, but
it has the pole at the same time.
Yeah, it will have exactly the same poles as what is expected from the amplitude, but it has no other non-analyticities. And the other representations always have extra non-analyticities. So what is the problem? So this is the Veneziano amplitude, which is a particular scattering amplitude in string theory. It's a ratio of gamma functions. So gamma functions, if you're not familiar, just to revise, the gamma of x actually has poles at x equal to minus n. So in my language here, gamma of minus s1 would mean that there are poles or singularities, the function blows up whenever s1 is equal to a positive integer including 0. Same for minus s2. And so this is what is called the Euler beta function. Euler was studying this in the 1730s. And the integral that he was actually trying to evaluate is this integral, which you might remember from your math methods course, but if you don't remember, here it is. And so when you actually binomially expand, so suppose I gave you this integral and I told you in some PhD entrance interview that evaluate this, the first thing that you would try, or you should try, is you binomially expand this and you integrate term by term. Okay? Don't worry about how legal that is, but let's do it anyway. And you're going to get a series representation where the poles in one variable is visible, clearly visible. And this series converges as long as the real part of S2 is less than 0. Okay? So if you put S1 and S2 in these expressions, and also in the series expression, such that the real part of S2 is less than 0, you'll get exactly the same answer as this. But the moment S2 is bigger than 0, it fails to converge. Now why is that? It's because S2 equal to plus integers, there are poles. There are singularities. And here, this guy is a Pochhammer symbol, and that's a polynomial. From a polynomial, you cannot recreate a pole. You require an infinite number of polynomials to recreate a pole. Okay, so there is no way that you can truncate this series and see the poles in S2. And similarly, you have the same representation in the other variable. So basically, in the standard textbooks, if you open Gratstein and Rijik, I don't know how many of you know what Gratstein and Rijik is, because you might be too young, but this is heavy, this textbook, which can be used as a paperweight or some weightlifting, but it's usually kept in any office in theoretical physics. And you open it and you'll get a table of formulas, and this is the usual formula that is given in Gratstein and Rijik. Okay? So this is the one channel. So remember that Dolan, Horn, and Schmidt had sort of alluded that the representation of this amplitude should just have one channel. And this is the formula that makes that intuition, experimental expectation or semi-expectation precise. But you open Gratstein and Rijik and you carefully stare at the integrals. There is another integral representation that is still there. You do some coordinate transformation from 0 to 1, and actually you get a representation which has poles in both channels, dressed by some polynomials. These are all polynomials. Remember, whenever you see a Pochhammer, this is called a Pochhammer, with a subscript positive integer, it's a polynomial in that. And there's another representation. So this is almost like quantum field theory, but not quite, simply because this also has non-analyticities whenever a real part of S1 plus S2 is bigger than minus 1. So this is not really what you would expect from quantum field theory either. Okay? But strangely enough, this formula is never mentioned in any string theory literature. So I never understood why. So in fact, this is only mentioned in a relatively unknown paper from 1971 by Nakanishi. And this paper just has one citation. Okay? So this is a new formula that we found using our techniques, which actually solves both these problems. First of all, this formula actually has these singularities in both channels. You're adding both channels, S1 channel as well as S2 channel. It is dressed by a polynomial. It has these extra pieces which look like contact terms, because whenever you have contact terms, you don't have any singularities. There's no exchange. Anytime you have a singularity, there is an exchange. No singularity means it's a contact term. Okay? This is exactly that property. Each piece here is actually analytic on its own, except for the obvious poles. It's analytic everywhere else. This representation is exactly what you would expect from quantum field theory. This representation does not exist in the literature, and the reason is because it uses a new form of what is called a dispersion relation that we established or developed over the last several years. Now, why is this important? This is important because the new formula suggests that there is a way to have good high energy physics but staying within the framework of quantum field theory. We can meaningfully truncate to masses within a certain energy window, and that's what you would like to do as a physicist. You don't want to carry the baggage of an infinite number of very high energy modes if you want to describe physics up to 10 TeV. But that is what string theory is telling us to do, that because you are summing over all the high energy particles with one channel, it will struggle to actually explain all the physics unless and until you retain all the high energy modes. So we can meaningfully truncate to the masses within a certain energy window. And these are some technical comments meant for the experts, but let me not go into them. And we can now begin to imagine strategies that rely on quantum field theory intuition and still explain hadron physics. So basically the main motivation is to see if we can widen the framework of this I should call quote unquote string theory, because it might not be string theory, it might be something else. Maybe the correct theory is a theory which involves surfaces, something, I don't know. But this is harder than it seems, and I will comment on this right at the very end. Yes?
Which idea that you would have had to, if you only get
Yeah.
Is it also related to this problem that you have in string theory of the
Yes. Yeah, so in fact, the relevant question that you have hit the nail on the head is that how much of the world sheet is actually needed to maintain these good ultraviolet properties that string theory has. And my intuition is that we should study this question more carefully. We really don't understand that. So it's not really an interlude, it's almost the end of my talk, but then what is it that made it possible? So let me just tell you some flippant remarks. So all this started with a grand goal. So the students who have worked with me know how I work. So we start off with a grand goal, and this was around 2015, 10 years back, to be able to calculate without encountering infinities that plague usual Feynman diagram calculations. Okay, and we had some success with students, Kallol, Apratim, this is Rajesh Gopakumar, not my student, but Parijat, who was my postdoc, and Kaushik, who was my student. We developed an algebraic approach to calculate critical exponents, and critical exponents, you think of water or superfluid helium at the critical point. And we found the Wilson-Fisher results in the epsilon expansion, so-called epsilon expansion, by solving algebraic equations which had no infinities. And we got some new results which were not possible using Feynman diagrams. And then we hit a roadblock that typically happens, and this roadblock led to despair, tearing hair, literally tearing hair, and frustration. And this lasted for around 3 years, and the lessons that we learned was that have a grand goal, and don't be scared to sacrifice a few PhD students. And although I should have a disclaimer that none of my PhD students were harmed in this endeavor, definitely pluck all the low-hanging fruits that you can, and as quickly as you can. And for this, have a good hair specialist and a psychiatrist. So definitely ask your institute to have both of them ready. And the less flippant comment is sometimes it takes many years for a good application to be found for a research paper. And thankfully, in today's day and age, hunting for hidden gems is easier. And around late 2020, in the middle of the lockdown, we uncovered one such gem by Oberson and Khoury, written in 1972. And when we located this paper, the paper only had 7 or 8 citations. And we built on this work in several papers here. And out of the blue in 2023, last year, a statistical physicist, and you can look him up, Chao-Ming Song, who's now a very good friend of mine, from Miami, built on our work for reasons that are, you should ask me later why he was at all interested in this, because he's actually a social physicist who's interested in problems like how COVID propagates and how to judge the impact of a paper using statistical physics ideas. And he publishes in some big journals like Nature and Science, but why he was working on this, I have no idea. He told me later, I'll tell you later as well in private, and found a very important simplifying step. And without all these pieces falling into space, the new formulas into place, the new formulas would not have been possible. So what lessons did we learn? Implementing this is easier said than done, because you are always tempted to judge a paper by going to Google Scholar or Inspire Hep and seeing the citations. I would say that don't just judge the paper by citations, read the paper. And that's why I said it's easier said than done, because there are hidden gems. How would you actually judge that this paper actually had anything of use? This, you just keep chipping away and hope for the best. And here, I don't know, I just wrote something. I was too tired. I couldn't come up with something clever to say. I said, hidden hand will show the way. There's a beautiful story using complex numbers, which I don't have time to go into. This is actually the development of these dispersion relations. So dispersion relations actually tell you how to apply Cauchy's theorem in a very clever way. I won't go into this because I have run out of time. But the simple thing is that a single variable Cauchy's formula looks like this. And basically, you have to specify 2 properties, the discontinuities of the function and what is happening. So basically, you think of this as high energies and think of whatever is happening as the spectrum. Okay, so think of the physics along these lines as a spectrum, and this is what is happening to the amplitude, scattering amplitude at high energies. And the lesson that you learn is that you can recreate the amplitude anywhere else by just knowing the discontinuities or how the amplitude behaves at the spectrum. And this is the 1 variable simple version which you learn in complex analysis. There's a 2 variable version which we developed, and it's too complicated, so I won't talk about this. The final neat trick which I have to say is that how did we introduce this parameter? The parameter was introduced by the following observation. So let's first modify the Euler beta function a little bit. So the Euler beta function was gamma of minus S1, gamma of minus S2 divided by gamma of minus S1 minus S2. I've introduced these parameters alpha and beta here. They are just fiducial parameters at this step. But the key step is to realize that once you introduce this, this has an enlarged symmetry. You shift S1 by S1 plus lambda and alpha by alpha plus lambda. This combination is left invariant. Similarly for this combination and similarly for this combination. And the point is that once you use this novel dispersion relation, you will see that the right-hand side is not invariant under this transformation. And as a result of which you introduce this parameter, this parameter here, lambda, into your formulas. So that is how we introduce this. This is how we found this unifying series, because now that you have a series, you should now ask those formulas that I showed you from Gratstrand and Rijik, are they actually lurking inside these formulas? And the answer is yes. Very simply, the single channel representation is simply found by just setting this parameter to minus S1 or minus S2. So what happens is, if you set S2 to be lambda, lambda to be minus S2, then this cancels with that and you're left with a single channel representation. Okay? And this kind of a picture actually asks us, begs the description of this. This is tied with your question, whether there is a real renormalization group reinterpretation of the results that we have found in the language of quantum field theory. This is a crucial step. So this actually suggests that there must be a reinterpretation of this formula in terms of a quantum field theory Lagrangian. Okay? And why this is powerful is that once you have quantum field theory, it's much easier to modify quantum field theory. It's much harder to modify string theory, but it's much easier to modify quantum field theory, at least on pen and paper. We have some new formulas for the zeta function, so I don't know what this is useful for, but I'm really hoping that some smart guy here will solve the Riemann hypothesis using this one day. But you can find this formula in our paper. So for example, it gives you a parametric representation of the famous Basel problem. It has a faster convergence than the usual series that Euler came up with. So where next? So this is where I'll conclude. And this is a problem for anybody interested in these kind of developments. The physics arguments that relied on field definition did not specify how many parameters we can introduce on truncation. And in the example I gave, we redefined one heavy field, but if we redefine an infinite number of heavy fields, in principle, there should be an infinite number of parameters. And that's peculiar, so that means that you can actually have these peculiar looking formulas for pi and zeta, which will have infinite number of these extra parameters like lambda, which have no role to play. And I do expect multi-parameter generalizations of the formulas we found, but I don't know how to get nice looking formulas except the ones that I showed. I should tell you that mathematicians have been very interested in these new developments. I told you that if you are interested, then you can go and find out more on Math Overflow. Rosengren recently gave a fresh mathematical perspective of the new formulas using a partial fraction technique. In fact, we immediately found an application from this new perspective. And this is a lesson that I learned. Thankfully, good science works through scrutiny and objectivity rather than prejudice and subjectivity. And this is something that is very hard to keep in mind while doing research in modern development, in the modern atmosphere, which is has changed drastically over the last several years. And what we are doing now, and which I'm very excited about, is with Faizan Devopriya, who's there in the audience, and Arnab, we are finishing a paper which will appear tomorrow on Monday, which enlarges the class of, and I call this string-like because I don't really know whether these have anything to do with string theory or something else. Using semi-definite programming and machine learning, who knows, maybe the experimentally relevant model is lurking in the space of these models. And this may be completely different from string theory. I'm quite agnostic about it. But I should actually point out one thing, that despite all the criticisms that string theory faces, it is still a very constrained quantum field theory, and not anything goes. And there are rules that are there which actually restrict the framework of string theory. So this is what is going to appear next week. And I will leave you with a thought. Surely we are not that arrogant to think that we have invented all the mathematics to understand the universe. Maths and physics must go hand in hand, and more dialogues are necessary. And this is something that we are discussing over lunch. Unfortunately, at least from my perspective, at least in India, this does not seem to be happening much. And I hope that the leaders would do something to change this. So thank you for your attention. Yeah, so that is why it is not the same as perturbative RG. So as I told you, I showed you the formula. So if you go back and showed, at least so far as pi is concerned, I had this formula right in the very beginning. Here. So here actually this is 3000, roughly what is this, 40, close to 40. And this gives you the same result. So in fact, I could put in lambda to be whatever I want. I could put in lambda to be complex, and still it is supposed to give you the same answer. So this is actually different. I use the words renormalization group to draw an analogy with what we identify as renormalization group in physics. So for example, suppose you're doing continuum renormalization group, not Wilsonian version, but the continuum version. You start off with the bare action. The bare action does not depend on this fictitious parameter. So whatever you have in terms of the bare quantity satisfies the same differential equation that I wrote down. So lambda is a fictitious parameter. In the continuum version of the renormalization group, you differentiate with respect to the fictitious scale that you introduce, and it is 0. So in that sense, it is similar in spirit. But I mean, exactly how they are related, one should look at the Lagrangian and work out in terms of the Lagrangian that I told you about. Which one? Oh, this is some random choice. You can put whatever you want. Yeah, I don't know. I have no idea. I mean, I don't even remember. But this formula is there. You can just play with it. Yeah.
So
Yes.
just a question about so the fact that in string theory you keep one S or the T channel. I mean, this is something that, for example, I think has passed me by in any understanding of the theory. So what does it do to the theory why is that required in the theory?
Yes.
At a fundamental level,
Yeah, so
and how does it constrain it? You said whatever you do now is
Yeah.
string-like theories. What is it about? Yeah, so maybe this is a longer conversation. But we can-
No, let me give a quick answer. So you see this integral. This integral is related to the world sheet picture. So this is an integral over the world sheet parameter. But this integral only converges provided your real part of S1 and real part of S2 are less than 0. And this is similar to this condition that we have for this series to converge. Okay? So to make sense of this integral, you only have one channel. So the world sheet picture actually requires you a description in terms of one channel. And then when you talk to experts like Ashok, they are going to tell you that there is string field theory. String field theory is like quantum field theory, so you should have all channels. And then you ask, where is this formula?
For an example, when we do particle physics, so let's say we have an electron-electron or electron-positron scattering. If we take only one channel, our answers, the scattering cross-sections comes up to be wrong.
Yeah.
So how can you say that we can take only some of one channels, then it will
Yeah,
come?
because actually what happens in string theory is that in order to make sense of this, you're not allowed to truncate this.
Okay.
So because as you see that this formula does not have any knowledge about where the poles in the S2 variable are. So if you just truncated it, it will definitely not know that there are poles in the S2 variable. Yeah.
Any other questions? If not, then let's thank Professor Sinha for the wonderful talk. Thank you. May I request Dr. Tarun to give a token of appreciation from RRI.
Thank you.
And thank you all for coming.
Thank
I
you.
think there's
Thank
a
you,
high
thank
tea. Right, yeah. So there's a high tea outside.
Thank you.
All right.
Yes, that's plug this. Here we have to press the knob. 3 seconds.
We were like wondering what string theory.